Hello everyone, myself Shikha, and I'm going to present the poster titled A Roadmap Towards High Efficiency Ultra Thin Flexible Silicon Solar Cell. My advisor is Dr. Sayak Bhattacharya. Why we are using this solar cell and silicon solar cell is because global energy demands are set to increase due to the rapid economic growth of the world. Currently, most of the energy is generated by non-renewable sources of energy, such as fossil fuels, coal, and oils. However, the energy production from non-renewable sources has a severe impact on the environment, such as pollution and global warming. So we are moving towards, to overcome these problems, we need to look at other sources of energy production, which is such as solar energy. And we know that over 173,000 terawatt of continuous solar energy strikes, strikes the earth, which is 10,000 times more than the worldwide power consumption. High efficiency and economically viable materials are needed to take advantage of incident solar energy to meet the energy demands. Now, why we use the silicon is because silicon is non-toxic and can be manufactured easily due to its mature fabrication technology. Still, a thin silicon slab is weaker absorber of sunlight due to its indirect band gap. Most conventional solar cells use a textured surface to maximize silicon's light trapping capacity, considering light as a rays. So the current world record single junction crystalline silicon solar cell is 165 micrometer thick and its efficiency is 26.7%. The maximum attainable efficiency is 32.33%, which is known as Quasar limit and also thermodynamic limit. So factors like imperfect light trapping and recombination in silicon degrade the efficiency of the solar cell. So there are mainly three types of recombination: Shockley-Ridgway recombination, Auger recombination, and radiative recombination, which take place in the solar cell. So till now, only ray optics based light trapping was used, and the maximum efficiency which can be attained is called the Lambertian limit. By considering light as a wave, as we know that light is an electromagnetic wave. So using light as a wave and using Maxwell's electromagnetic equations, we can look for alternative architectures such as photonic crystals, which maximizes the light trapping. So recent advancement in photonic crystal-based solar cell predicts efficiencies over 30%, which is well above the Lambertian limit, and even use very thin materials which can be flexible and of lesser cost. So here we investigated thin films, a thin 10 micrometer solar cell, silicon solar cell that uses a layer of anti-reflection coating and wave interference-based light trapping in carefully optimized photonic crystal cell that surpass the Lambertian limit. We use the MAPDs and absorption profile obtained by solving Maxwell equation as input to the carrier generation and carrier transport equation for the solar cells. A low doping level in the p-type bulk and bulk crystal ensures low Auger recombination. The top and rear of the cells are diffused with highly doped donor type and acceptor type impurities respectively, to form conformal N plus and P plus layers at the two ends of the cell. This provides a front surface field and a back surface field to deflect minority carriers from the surface and contacts. Our electronic design is similar to the conventional passivated emitter, which is a rear totally diffused architecture. However, because of the reduced Auger recombination in our thin silicon cell, we predict a power conversion efficiency higher than that of the best available pulse cell. Using the optimized doping parameters for FSF and BSF region, we calculated the JV characteristic of our proposed cell with different thicknesses. While thick cells in general absorb more sunlight for higher saturation current, the increased non-radiative bulk Auger recombination leads to lower open circuit voltage and lower conversion efficiency. We saw that the 10 micrometer is optimum cell thickness for inverted pyramid photonic crystals. And here, so we saw that in this we use SiO2 layer at the back for the passivation, and it is 720 nanometer thin and plus region. So then we saw that the variation of the spectrally resolved current density with the wavelength of light for different thicknesses of solar cell. Why this spectral response? Because this is conceptually similar to the quantum efficiency. The quantum efficiency gives the number of electrons output by the solar cell compared to the number of photons incident on the device, while the spectral response is the ratio of the current generated by the solar cell to the power incident on the solar cell. So in this, we can see that the current density is not dependent on the cell thickness for lower wavelengths of light, but it increases with the increase in thickness for the higher wavelengths of light. So this further improves with the photonic crystal cell. After that, we saw that the variation of absorption of light for different thicknesses of solar cell. Here we see that the absorption of light is also higher for the higher wavelength and thickness of the cell as compared to the lower wavelengths, where it is independent of the thickness of the cell. The variation of maximum achievable photocurrent density, different thicknesses of solar cells. So here we use the equation of maximum achievable photocurrent density, that is from this integral, where I lambda is the AM 1.5G intensity curve for the AM 1.5G spectrum. And it is observed that the maximum achievable photocurrent density changes sharply for thin Lambertian solar cell compared to the thick Lambertian solar cells, where MAPD is almost saturating. The MAPD for photonic crystal solar cell also varies with the thickness of the cell, and it gives better efficiency than the Lambertian cell. Here we have simulated 1D ultra-thin 10 micrometer photonic crystal solar cell with a different doping concentration of N and P region. So from this we get this a JV and PV curve for the simulated structure, where the where the short circuit current is 42.5 milliampere per centimeter square, and we calculated the fill factor, which comes to 87.2% and efficiency of 29.6%, and also the open circuit voltage of 0.79 and equivalent to 0.8 volt. So thank you for listening.